Good morning, all.
Yeah,
Good morning,
please.
all. Let's begin. Let's continue what we are doing. So we were doing mm, semi-simple algebras. It's representation theory. Uh, it's finite dimensional semi-simple algebra over complex numbers, and the representation theory is highly dependent on SL2 theory. The SL2 theory, we can use it because in semi-simple Lie algebra, so there are many SL2 copies are there. So that's what so for that purpose, we fixed a Cartan subalgebra, which is like in GLN. So H is like diagonal matrices, all diagonal matrices. And we consider the adjoint representation, and using the preservation of Jordan decomposition. So G will split into root spaces, and zeroth root space is H itself, and the remaining roots are form a root system. So um, you can make them, some of them, they can declare that some of them are positives, and exactly the negatives of those roots are negative roots. So this is a triangular decomposition of you have it, and which is same thing as for SL and C. Uh, you know, uh, lower triangular direct sum with diagonal matrices, strictly lower triangular. So these are strictly lower. And n plus is strictly upper triangular. Okay. Now the beauty here is there is an SL2 copy here. So corresponding to G alpha. So there is each root, there is a E alpha exist, and in its negative there is a F alpha exist, and these two span an SL2 copy. So in particular, the Lie bracket is we denoted by H alpha, which lies in H. So these two F alpha, E alpha, H alpha, and they give a basis, and it is an SL2 copy, and which we denote by SL2 alpha. So this is an SL2 copy which sits inside a semi-simple Lie algebra. There are many SL2 copies, as many as a number of positive roots. So we want to use these SL2 copies to study more about representation theory of G. So what we begin about representation theory. So we started with so our goal is to classify all finite dimensional irreducible representations. That's good enough for all to get all finite dimensional representations due to Weil's theorem of a semi-simple Lie algebra. So what we did, we begin with a finite dimensional representation, and then that row, so you restrict it to adjoint action, that Cartan subalgebra, it's a representation, so there is a row from G to GLV. So when you restrict it to Cartan subalgebra, so this V can be break down into direct sum of simultaneous eigenspaces, and the eigenspaces, the eigenvalues are now each element of, like a diagonal matrix, there is a scalar. So for all the elements of H, you have to associate a scalar. So mu lies in H star. And what we did, we took a weight vector in some V mu. We keep hitting on E alphas. So so we took some vector exist in V mu, So we keep hitting on E alphas in some order. Then eventually you get a vector because of the finite dimensionality. You get a vector which is still an eigenvector, because when you act with E alpha on a weight space V mu, the resulting vector has a weight V plus mu alpha. So the weight is increasing by alpha. So then eventually you get a vector which killed by all the E alphas. So you can't talk any E alphas at all. You get a 0. That means for this lambda, so for this lambda plus alpha will never be a root, never be a weight. So that's why this V is called highest weight, because you can't add anything to it. So that lambda is called a highest weight. And such V is called highest weight vector. And so because of this, so finally what we have seen is the V looks like, it actually a representation of G. It is a cyclic representation. We have begin with irreducible representation. So if you begin with irreducible, then it should be cyclic. And then you got some V lambda. So let's denote by this V lambda, some vector. Now, because all E alphas are killing, so it only by PBW theorem, you arrange a basis such a way that first there are E alphas, then there are H alphas, then there are some F alphas. So that way you can add it. So if you arrange like that, then this E alpha will kill them. So that will, then H alpha will fix V lambda. So only F alphas will remain. So this is same thing as UN minus V lambda. So that's only F alpha should act it. So you have a PBW basis for UN minus. So this is spanned by so you have a base, you have a spanning set, but which is infinite dimensional. Infinitely many vectors are there. So there are a bunch of, so there is an order for F alphas. For example, if you took it SL3, SL3C, so you know F1, F2, F theta. So if I keep this order and you allow some powers of them, and IJs or anything, any non-negative integers. So this is a spanning set. So this is so it is very clear that many of them will become linearly dependent. So it's a finite dimensional finally. So we'll discuss what we have to show now. Where are we? So this is what we did it last time. So given any finite dimensional reducible representation, there is a weight vector exists. Even furthermore, we studied that. So that weight vector, if you restrict it to SL2 copy, so at present lambda is in H star. So at present lambda is in H star. But if you restrict it to finite SL2 copy, so by restricting to by restricting V, to instead seeing the entire SLG representation, if you restrict it to SL2 alpha, what we concluded that the lambda should have on H alpha, it should have non-negative integers for all positive orders. This is just SL2 copy. SL2, whatever we did, we have seen in SL2 representation theory. So I did the same thing. So I got this. So my goal now is, so that's what we did. So my goal is, so I have associated this. So I want finite dimensional irreducible representation of G up to isomorphism I want to classify. And they are in bijective correspondence with. So what we got is the weight, I got it. The weight has a property that lambda of H alpha is non-negative for all alpha greater than 0. And I want to show that this is a bijection. Okay. So far I have taken a V, I have associated a lambda. Okay. So I want to show this is a well-defined map. So claims are this map is well-defined. This map is 1, 1. This map is onto. So these are the three claims we are going to see now. Before going further, I think let's analyze, let's understand this set. Okay. What is this set in SL3, for example? So lambda is in H star. Okay, so lambda of H alpha is, so maybe it is a, see this H alpha notation, Sachin used as alpha check. Okay, so which is same thing as alpha check. It's a coroot, which is coroot which lies in H, coroot to the alpha. Alpha lies in H star. So lambda of H alpha is same thing as lambda of alpha check, which you have seen is 2 lambda alpha. So here the killing form. There you have seen the inner product. And what is that lambda of H alpha greater than or equal to 0? The same thing as not this is an integer, but moreover this is a positive number. So this is a greater than or equal to 0. If it is for all positive roots, then this is all for positive roots. So what you are getting this lambda.
Ravinder,
please.
This actually in my notation, alpha check is in the dual. Actually,
okay,
H star.
Okay.
And so
Okay.
this is just you are identifying double dual with these things.
Yeah,
I think so. Just
okay.
Wanted to clear the confusion. Actually, yeah. Okay.
Okay. Thank you, Sachin. Yeah. Okay. So what you have right now is lambda with all positive roots is greater than or equal to 0. Have you seen such things? So you remember once you studied root systems, an element in H star, or in your notation, it is in E in the root system. So that's what he is telling. So he is telling that this is in E star in his notation, and these are in E. So that's the notation of Sachin. Let's yeah, you have an element of E which is positive with respect to all the positive roots, which is non-negative. So that is called lambda lies in a fundamental chamber. So this is the definition of, that's how the fundamental chamber is designed. So lambda lie in a fundamental chamber. I think this is a notation. I don't know what notation he used it, but I draw the same picture which Sachin has drawn. Let's draw the chambers for A2. So you need a, okay. So this, there is an alpha 1 here, and there is an alpha 2 with the same length, but angle is 120 degrees. And when you add it, you get alpha 1 plus alpha 2. Right? My picture may be not correct, but then the hyperplanes, if you draw it, so if you draw the hyperplane of alpha 1, so this is H alpha 1. This is hyperplane which is perpendicular to alpha 1, and there is an hyperplane perpendicular to alpha 2. Yeah, maybe my picture didn't well, but there should be something perpendicular to alpha 2. Okay, so my picture is wrong. So what shall I do? Okay, so this is a bad one. So this should not be perpendicular looking like. So what to do? So this should look like perpendicular. So let's okay. So the first I draw the perpendicular to alpha 2. So my theta should lie in that. Right? So this is a perpendicular, let us say. And my theta should lie in that. So that means if you add these two, it will be somewhere and then maybe I'm not drawing correctly. So that's but any case. So this is a if you recall is a thing. So there are many hyperplanes are there. I have drawn H alpha 1 and this is H alpha 2 and something in this is a fundamental chamber. So what is this fundamental chamber property? Even there are 6 chambers are there. So there are 6 chambers which you have seen already. So among the 6 chambers, this is a fundamental chamber. The property of this chamber is anything here. So lambda, so the conclusion here is lambda is lying in this. So what is lambda coming from? Lambda is should be in H star actually, but right now we concluded that it will lie in the fundamental chamber. The property of fundamental chamber is on all positive roots, it's non-negative and it's integer. So it's not on this entire fundamental chamber, only at integral points. So that's where the lambda lies. That is the highest weight means. Okay, so that we should clear. Any yeah, you okay? So this is about lambda. Lambda lies here. And what else I want to tell about lambda? So I think you can define if before going. So there are natural fundamental weights, namely omega 1. So there's omega 1 which lies in what is omega 1? So first thing is it's enough. So lambda is a, maybe I'll write it on here. So lambda is, so maybe I'll create a notation which is lambda plus. By definition, this is set of all fundamental, set of all dominant integral weights. So this is in H star, which have this property that lambda of alpha or H alpha is greater than or equal to 0. But it's easy observation that you don't need this all things because every positive root. So this should be actually I supposed to write for all positive roots, but it's every other H alphas are linear combination of simples. So just make simples are good enough. So lambda of hi, right? In SL3, if you remember, h1 plus h2 is h theta. So that's why just h1, h2 are good enough if L is the rank. And then there are some natural things which you can define, omega 1, so which is dual to the h1 2. So omega 1 and omega L, they belong H star, they are dual basis of h1 to HL. What is the meaning of that? So omega 1 and h1 is 0. Omega 1 and all the rest of the, sorry, omega 1 h1 is 1. So on 1 and remaining all the things are 0. And similarly, omega 2 on h1 it is 0. On h2 it should be 1 and remaining all are zeros. So what is the use of this? So where are the fundamental weights are lying in this picture? So the fundamental weights are, it is on h2 it is 0. So it should lie on hyperplane corresponding to h alpha 2. So this here. So with a so this is a omega 1. Omega 1 has a unit distance with so omega 1 on h2 it is 0. So omega 2 which lies in it should lie in this chamber definitely. Omega 2 is on h1 hyperplane. So h alpha 1 is here. So something here is omega 2 with the same distance. Okay. So they are the ones which are fundamental. And what is the claim? Any lambda can be written as some non-negative integer linear combination of, so maybe lambda may be some 3 omega 1, I don't know. So maybe something maybe 4 omega 1 plus 3 omega 2. So something like this. Every lambda looks like this. So it's very easy, right? So what you are seeing, so the observation here is If lambda is in lambda plus dominant, then lambda can be written as on each hi it should be a non-negative integer, right? So on each hi it should be a non-negative integer, and this omega s are exactly on hi it takes 1. So if you really want, actually this is a lambda of h1 omega 1. So you can in fact write this. Right? So the moral is this can be identified with, right? So some non-negative integer lambda of z1 times omega 1 plus right? And what you have seen in SL2 copy, so the SL2 you have seen that these irreducibles actually corresponding to z greater than or equal to 0, right? So this is the same picture, right? So you are in a same picture now. Finite dimensional irreducibles of SL2C are actually corresponding to non-negative integers. Now what you are doing is finite dimensional irreducibles of G, which is a semi-simple Lie algebra, are actually bijective correspondence with some product, some how many? L many. L many. What is a L? L is the dimension of H, so which is rank with rank L. So for example, SL2C has only one dimensional kata. So that's why there is only one non-negative integer. But if there are many dimension katan is there. So for example, SL3 has two basis vectors in the trace zero diagonal matrices. So SL3 is rank 2. So it corresponding to product of two non-negative integers. Okay. So far, so good. What else I need? Okay, so this is okay. This is what I want to show. Now, where am I? So I have to prove this. This is well defined 1, 1 and on 2. That's a map. So for that purpose, I need to understand this. I need to understand such modules. Right? What is such module looking like? Such module, this V has a property that there is a highest weight vector, and it's a cyclic module generated by highest weight vector. Okay. Forget about irreducibility. You have so just such modules are called highest weight modules. Okay. So the highest weight modules are may not be irreducible all the time, but you want to study about even these irreducibles, but you are observing that V is exactly the highest weight module. So highest weight module means this is the definition. So if you want to formally write it down, so whatever highest weight module means, there is a weight. So maybe I'll tell you here. There is a weight vector which should be highest weight. Means you can't add any plus alpha to it, plus positive root to it. Means any E alpha, it actually lies in the weight space lambda plus alpha, but that weight space should not exist. So no, not that way. That weight space may exist, but this no. 1 second. E alpha, that weight space. May exist by some other vector. Yeah, for this vector, it should not lie. So I'll repeat again. There's a weight vector lambda. Its highest weight vector means on this any alpha should kill it. Okay, so that's why this vector will not lie in any lambda plus alpha weight space. Okay. So then it's a cyclic module as well. So maybe the definition. So I'm just dropping the irreducibility. I'm just studying the highest weight modules. By definition, if V is an highest weight module, so the definition is V should look like it's a cyclic module, and this is an highest weight vector. Means it should be an highest. It should be so just HIs are good enough, or H alphas are good enough. So means HIs are good enough. I just wrote H alpha. and then E should kill it. Okay, so there should be an highest weight vector exist, and then V is a cyclic generated by that vector. So the beautiful property is, we have seen that it is a un minus v lambda. We have already seen in SL3 situation that it is spanned by the bunch of Fi's, right? So when you see bunch of Fi's, I am just drawing F theta. These ij's are greater than or equal to 0. They act on some v lambda. So what you are seeing here is the weights. So v is direct sum of weight spaces. See, you are seeing everything here. It's spanned by these things, and everything here is a weight vector of weight lambda minus some I1 alpha 1 minus I2 alpha 2 minus I3 theta. The theta is alpha 1 plus alpha 2. You can club together alpha 1 plus alpha 2 to this combination. So it will be, the weight looks like lambda minus K1 alpha 1 minus K2 alpha 2. So what is this weights? So the weight looks like this form. Okay, and there is a notation for this. That is exactly same thing as mu is less than or equals to lambda. What is the mu is less than or equals to lambda? That means lambda minus mu should be, this k's here are non-negative integers, because ij's are non-negative integers. So k's are sum of the ij's. So lambda minus mu, if you do it, it is a in the non-negative integer linear combination of alpha i's. Right? So this is a, so this notation means I am just telling that the mu's are lambda minus some non-negative integers of linear combination of alpha i's. So far, this is what you get it, and what else? What property you get it? So the another property you get is each weight spaces, they are all finite dimensional, right? So you have seen that the weight looks like this, right? Means you can't hit infinitely many to the v lambda. So because there is a bound for alpha 1, alpha 1 should times only k1 times, alpha 2 should come only k2 times. So there is a bound here for alpha 1, and that, so this k1 k2s, if you fix it, that's what mu is fixing means. Once you fix k1 k2s, so there are only finitely many chances for here. Maybe you can take maximum of ki's, you can take it. Right, so that is maybe k1 plus k2. So you can take k1 plus k2. Each one you can't hit that much is a bound for that. So you can't, I1 is less than or equal to k1 plus k2, I2 is less than or equal to k1 plus k2, I3 is less than or equal to k1 plus k2. That will be the spanning set for this v mu. So there are only finitely many vectors. So that's why this is although this v may be infinite dimensional. So I'm not even assuming V is finite dimensional here. I'm not even assuming V is irreducible here. I have only highest weight module by definition. It is a cyclic module which is generated by some highest weight vector. Okay. So it could be finite dimensional, it could be infinite dimensional, it could be irreducible, it will be may not be. So the properties here is, the first property is it's the direct sum of weight spaces. Weights are less than or equal to lambda. Second properties are weight spaces are one dimensional, finite dimensional. And what about this V lambda? So what is the dimension of V lambda? Lambda's weight space, right? So if you see this every vector, so weight vectors are here. If you want a lambda weight, you should not hit anything, any F alpha should not hit it. But once you start hitting with, then lambda weight will start decreasing. So only V lambda and its scalar multiples will give you the weight of lambda. So dimension of V lambda should be 1. So what else? And third property, every submodule W is also can be decomposed into weight spaces. So V has a weight space decomposition, and the same weight space decomposition, in fact, if you can restrict it to any submodules. Okay? So this we'll see in the tutorial why this is. And then the fourth property is, so this property will tell you that if you have a proper submodule, it should drop V lambda. So it should only contained in the V mu's mu strictly less than lambda. Because every submodule, so this is exactly telling you that every submodule will lie here. Right? So you can add all the submodules. So there is a maximal submodule. If you keep adding it, still they'll lie in only this. So you can take all the sum of all the submodules, you can take it, sum of all the proper submodules. So that's why there exists a unique maximal submodule. What is the unique maximal submodules? You take one sub, you take all the proper submodules, maximal proper submodule. You add it, so that will be proper again, right? Because of the same reason. They all lie in only this space. They will not capture the lambda. So because since you have the unique maximal proper submodule, you can quotient by that. So that will be the unique irreducible quotient. Right? So these are some properties of highest weight vectors, which are useful because we'll see the use of them. So right now I'm going back to my setting. The only thing my setting has a different is, so my setting has, this is a highest weight vector, but the extra information I'm assuming is it's finite dimensional, it's irreducible, and it is an anyway highest weight module. So my claim is this map, whatever you have associated to some dominant integral weight, right? The lambda, this is a well-defined map. What is the meaning of well-defined? Well-defined means you have to associate it to an highest weight vector, the weight of an highest weight vector. So can V has some other highest weight vector? Who knows? So that's a question. Right? So does V, okay, suppose it has a highest weight vector, V lambda. In fact, because it's highest weight vector, it's a UN minus. Suppose it has another highest weight vector, some W mu, right? So can this map to mu? So that's the question. Well-definedness means we may have many highest weight vectors, right? So that's a question. Where do you map? Which weight you map? That's a question. But you have to show that no, there will not be any highest weights existing. Because the reason you are seeing is this implies, right? So these two are equal. Means somehow you should get this muth weight space by eating some F alpha. So for example, this implies muth weight space should be less than or equal to lambda. You keep eating with F alphas, you get lambda. And this implies lambda weight space you should obtain from, because this is equal, so you should obtain from mu. So this two implies lambda is equal to. Right? So you know the SL2 picture, lambda, you can go by this direction by minus alpha 1. So this is F alpha 1, this is F theta, and this is F alpha 2, right? That's how the highest weight begins. So mu cannot be somewhere here. Mu cannot be in the down. If mu is here, means there is no other highest weight exist. If mu is here, you can't get the lambda back because lambda should also be there. So because your directions are only down, not the up. Okay, so this is well defined. There is a unique highest weight exists. Okay. So now it's 1 1. So what about 1 1? So why it is 1 1? What is the meaning of 1 1? If two irreducibles are there, finite dimensional irreducibles, if they map to same lambda, then your claim is V is isomorphic to W. That's a 1 1. So this is up to isomorphism you're proving. Okay. So this is the 1 1. What is the meaning of same highest weight vector exist? So my V is some highest weight module with some V lambda. W is also an highest weight vector with may have same lambda as highest weight. Right. So then what is the problem, right? So then the problem, the worry here is maybe you consider V direct some W. This is also UG module. Right. So this is not equals to, so this is not a cyclic module, may not be cyclic, but if you look this space, right, this will sit here, but this is whatever you are seeing here, this is the highest weight module, because this is again a weight vector, highest weight vector, because this kills by all E lambdas, this kills by all E lambdas, this will kill by all E lambdas, and sum of two eigenvectors is an eigenvector if they are same, if they are eigenvectors for same eigenvalue. So they lie in the same eigenspace. So this is a same lambda eigenspace. So this is a highest weight module. So it should have a unique quotient, unique irreducible quotient. That's a fact. So that's what you have shown here. Every highest, so this is a property is useful for me. Every highest weight module should have a unique irreducible quotient because it has only unique maximal idea, maximal proper submodule it has, unique. So you basically you take the projections. This projection, while you restrict it to this subspace, so what do you get? If you projection from UG, right? It goes, so you're restricting to this. And where is this V lambda plus W lambda going? It is going to V lambda. That's a projection map. So it's a non-zero map. So any non-zero map, it's a surjective map, because V, I know that it is a UG V lambda. Generator is mapping to generator. It's a non-zero surjective map. So it might have a kernel. So that kernel, I don't know about this irreducibility of this module. So this module I don't know. So it will have a kernel. So some maximal submodule it have it, which is isomorphic to that V. Okay? That's the subjectivity is there. From here to here, there is a surjection. And if you do the same process, so you project it to second coordinate, what do you get is this by some other maximal submodule, but there is a unique maximal submodule. The same thing should be isomorphic to W. So that forces that these two are isomorphic. Because the only thing I'm using is this is an highest weight module. It should have unique maximal submodule. Okay. Because projection 2 is also gives a onto map from here to W. So once you have an onto map, there should be a kernel. That is because W is irreducible. You have started with V and W are irreducible. So the kernel should be a maximal submodule. So, but this one will not have two maximal submodules. It has only unique maximal submodule. So that these two are isomorphic. Okay, so one oneness is done, well defined is done. So the thing now is onto. So that takes more time. Right? So onto, what is onto means? Onto means given a dominant integral weight, how do you construct a finite irreducible module? So this is a construction. So you have to construct some modules for G, right? So this is where This is where the UG information is very useful. Right? See, constructing modules, if you have a ring, for example, constructing a R module is very easy, right? So one of them is, let's say, you just take by quotient by left ideals. This is, so I is a left ideal. And armada is an R module, even cyclic R module. So it's a cyclic R module with generated by 1 plus I. So it is a so R mod I, it's a left multiplication map. What is a map here? So it is a module, right? It's a left multiplication map, and so that it is generated by 1 plus I. So that is the use of having a rings. So if you have a ring, it's easy to construct a modules for rings. So just by quotient by some left ideal, you get a module. So I know that G modules are representations of G are same thing as modules for UG. Right? So if someone asks me to construct a representation, oh, I quotient by some ideal. That's it. So I just need to quotient by some ideal. Okay. So but the I want something more than that. So what I want? The quotient should be such a way that, so given a lambda here, I should construct a module whose highest weight is lambda. So you want these properties. You want the because it's a bijection, I want it. So the lambda is obtained from the highest weight module. So I have to construct a highest weight representation, highest weight module. So what is that highest weight module means? So the extra, so given lambda, right? I need actually in lambda plus, but forget about lambda plus. It's even H star. I can construct a module. I want to construct a module UG by some ideal I have to quotient. So the what properties you need it? Some ideal I have to quotient. That's correct. What properties I need it? So this is a UG module, which is a cyclic module generated by 1 plus I lambda. The properties I want is the generator, whatever cyclic it is, should be killed by all the E alphas. That means what? Killed means it's 0 plus I lambda. So that means E alpha should belongs to I lambda for all alpha positive. And one more relation is it should be an eigenvector. So H dot H alpha dot, it's a left multiplication map here. So H alpha, so you want this should be equals to lambda of H V, right? Now what this means, H alpha minus lambda of H alpha times the 1, which is in the ring, should be in the I lambda for all alpha positive. So the I lambda has the minimum these conditions. If you want highest weight module, you can quotient by any left ideal, but then you get a module. But if you want highest weight module, you have to quotient by at least these relations. So that at least relations are I'm calling as, so what is now I'm calling as a Verma module. What is a Verma module? Given lambda in H star, I am constructing a M lambda. This is by definition UG. You quotient by left ideal generated by, so it's a left ideal generated by E alpha should be there. H alpha minus lambda of H alpha times 1 should be there. So this is the minimum conditions you needed to get a highest weight vector, highest weight module. Right? So this is a minimum you needed to get a highest weight module. That's what you did. Okay. But the thing is, this could be very big. So for example, even in the SL2, so even in the SL2, what is our Verma module? Let's say lambda. Lambda is in H star. Lambda is in H star. So maybe lambda, you can take n. You have seen, right? So this correspondence, when I write z greater than or equal to 0, I replace with omega once. When you want H star, you can take a non. So either you can take n or n omega 1 if you want. So the omega 1 has a property that what is omega on H1? So it has to go to 1. So this is anyway. You can assume as n if you want. So if you are familiar with n, so mn, I'll call as mn. In SL2, what is this telling? So this has to kill by. So there is a. So this has to kill. So let's write down v lambda. So my notation for v lambda is this 1 plus I lambda. So what is v lambda? So you declare it with 1 plus I lambda, and the relations. This is I lambda. I of lambda, I suffix lambda. What I'm using I lambda. So what else? In other words, to write, I think this is if even here itself. If you take small v lambda as 1 plus I lambda, what you are getting is m lambda is a cyclic module generated by v lambda such that E alpha should kill it. H alpha should act as lambda of H alpha v lambda. This is what you want it to be an highest weight vector. And this is what you are getting by this construction and nothing more. Means no other relations. Right? So only these relations are there. So they may generate some other relations. Let's look what relations they may generate or not. So Mn. So E alpha killing, E killing, F is H is fixing. So the what is that PBW basis will tell you that only F's can act. Right. So this is a spanning set. And in fact, it's a basis because they're all weights are decreasing. Nothing, no relation. So it's in fact no relations are there. So this could not be zero vector because the relations are only there. Only these on E alpha should kill, H alpha should kill, but these relations will not generate these relations on F. That's a Verma module very special. That's exactly the proof. If you want to use it, it's exactly the PBW basis proof. So PBW basis will allow that these relations. So my claim or observation that some F alpha is killing. That means what? So what is the relation you want? F alpha, you want to be here. Some power should be here, right? F alpha, some power will never belongs to left ideal generated by this. F alpha, some power will never belongs to left ideal generated by this. It's actually a PBW basis. It's very useful. Okay, I'm not telling it, so I'm not giving proof. It's exactly the PBW. You have to order the UG. Left ideal means you are hitting with UG. You have to order the basis with some UN minus and UB. That is so it's some computation you have to do, but maybe just believe that. So these relations will not give another relation on F alphas for killing. So they all will never be equal to 0 in Verma modules, right? So this is the Verma module will never be equal to 0. That's what I want to, because I'm not imposing any other condition. Okay, but I want, this is an highest weight module. So this highest weight module will have a unique maximal submodule, and that submodule, if you quotient it, you should get back my irreducible representation corresponding to n. That's how. See, you remember where I'm on to next, how I started? I have to take a dominant integral, right? I have to construct a irreducible representation. To construct irreducible representation, in between I am using Verma modules. They have no other relations except the minimum, the highest weight representation I wanted. So only those relations are imposed. So it is an infinite dimensional space. But it is being an highest weight module, it has a unique maximal quotient. That unique maximal quotient, you divide by it. That gives a irreducible representation. The weight will be same as whatever weight Mn has. So Mn has n. So let's forget this, and this is a Vn. You call as so Vn. Okay, anyway, so this is Vn. Right. So the weight is the same weight. So the highest weight will not change if you quotient by because it is generated by Vn plus that maximal height. Okay. So this is the construction. I want to go through this construction for SL2 once, and then we will see for in general. So SL2, so what I'm doing now, this has a unique maximal submodule. What maximal submodule it has it? So that's a question. Maybe I will not put n here. So I'll take lambda as a complex number. Because I defined Verma modules for any element of H star. So this any complex number makes sense. Okay, so then it is a V lambda by definition 1 plus I lambda, and this are killing, they are all infinite dimensional. These all are okay. Now the question is, what is the maximal submodule it exists? If lambda is a complex number, what do you mean by maximal submodule? The maximal submodule should have a weight vectors. We have shown already. Suppose suppose this is a weight vector. If suppose this belongs to maximal submodule. I'm repeating again. I want to analyze Verma modules for SL2. I have defined, and there is no other relations for F, so it's an infinite dimensional space. I want to quotient by its maximal submodules to get irreducible. So I'm understanding its maximal submodules. Maximal submodules, any submodule of highest weight module has a weight vector. So fix one of the weight vector. These are the weight vectors. So fix one of the weight vector. Suppose this vector is there. Now what module I get it? So what is so the maximal submodule, right? Submodule means on this vector you can hit with E, F, H, that still lies in maximal submodule. When you hit with H, there is no problem. It's a weight vector. It is a fixes. When you hit with F, it go back. And then on this, you can hit with F. So all the left side ones Fs should be there in the maximal submodule because of it's a submodule and it has one I weight vector. So everything left side should be there. What about the right side? The right side will obtain by hitting with E's. When you hit with E, I know that I will get this, but with some scalar multiple. If that scalar is 0, then I can stop this process. I don't, if whatever, if I act with E, maybe I should take this. Yeah, so if E action, I have to worry now. So what scalar I get it? So you remember what E act on F over K V lambda? That is by definition, or some calculations you did it in your SL2 computation. It's a K times lambda minus K plus 1 times the below vector. Okay. So this goes to this with this scalar. Okay. If the scalar is 0, then only I take the left sides, only I take these left sides. That will give you a maximal submodule. But when this scalar will be 0, the scalar will be 0 if and only if the lambda is equals to K minus 1. Means the K is an integer there, non a positive integer. So lambda should be greater than or equal to 0. So this concludes that m lambda will be an irreducible always. There is no maximal submodule if lambda is a complex number, but lambda is not a non-negative integer. So this is where we are going towards, in fact. So in general, we have constructed lambda highest Verma modules for any complex any element of H star. They themselves may be irreducible. That's a beautiful. Okay? So it doesn't have any maximal submodule here because E's also will generate full. So E's will generate full now. This is not a. So you get entire module. The scalar will never be equal to 0. So the scalar will be 0 in this situation. So that if you capture that information, what you are telling is if lambda is equals to some n, which is a non-negative integer, what you are telling now, f, which one is killing now? F power. So what you are getting now is f power k v lambda and E acting going to 0. So what you are getting here is E acting on f power. What is k now? Lambda plus 1. So n plus 1 dot Vn is equals to 0. Right. So if you don't want to use n, it's okay. That's okay. So maybe I'll just put a lambda as it is. I'll have it. So if lambda itself a non-negative integer, then what you are getting here is E dot f power k is now I'm seeing here. So this is 0. So e power lambda plus 1 should kill. Once this is 0, what you are getting exactly is m lambda has a unique submodule, unique proper submodule, has a unique non-zero submodule, because you want left side everything should be there, namely this one. So you namely this will become, so you stop here. What is this stop? F power lambda plus 1. So you are going to stop f power lambda plus 1 dot v lambda, then f power lambda plus 2 dot v lambda. It's going on. This is a maximal submodule. This is a submodule because of this. E is killing that. So E usually pushes to the next, right? But here E is pushing to 0. So this will be a SL2 submodule. Okay. And now you quotient by this. So this is you're calling as I lambda. No, this is lambda. So this is not this is a submodule, so it's a n lambda. This is a maximal submodule. And now if you quotient by m lambda by n lambda, only the remaining basis vectors you get it, namely v lambda to this v lambda plus n lambda. You have to make it plus n lambda. F power lambda v lambda, and this is exactly isomorphic to, if you remove that n lambda, it's exactly looking v. So this is the irreducible you are getting it, which is equals to v, which is v lambda. Okay. If you remove this, so what you are exactly seeing as the v lambda construction means, but you don't know at that time. You know how to construct this v lambda. Maybe you did it in SL2 theory. Yeah, you have constructed so v lambda with this basis. Here we have constructed another way. So this is a construction by using Verma modules, you quotient by the unique maximum submodule. Okay, perfect. Now I want to do the same process for in general for any SLN. Before going for SLN, this observation, whatever we made it, right? Even for SL3C, even in general for any SLN. Uh, SL3C, what it is telling, what is M lambda, right? So M lambda is spanned by, there is a V lambda, you can hit with F1 lambda, you can hit with F2 lambda, you can hit with F theta lambda. Right? These are all ones, you remember, right? It's a spanning by bunch of F's you have to hit to the left side. So I'm listing them. One time I hit it. So this is the order I'm, so maybe I'm M lambda is U n minus some V lambda. The n minus ordering I am making as by PBW theorem, F1, F2, F theta. This is the order I'm making. So there are 3 positive roots are there. I have to hit with some powers. I3, some V lambda. Once you hit with that powers, what I'm getting here, so it is you have to hit with F1. So F2, first you hit with I1 is 1, I2 is 1, I theta is 1, rest of them are 0. Then 2 times you can hit. So F1 square you can hit, F2 square you can hit, F theta square you can hit. And what else? 2 times you get it. So F2, F1 you can hit. So for example, you again get F1, F2. You can get F1, F theta. You can also get F theta, F2. So okay. So I'm just writing the spanning set for M lambda. I want to analyze the same theory, whatever I have did it here. So whatever I did it, I wrote a spanning set for M lambda. And this theory, so somehow I should, what is my goal actually? What is my goal? My goal was, if lambda is in a dominant integral weight, means if lambda of H alpha is non-negative integer for all alpha positive, I have to construct an irreducible representation, which is V lambda, right? What I have constructed is M lambda, which works for every H star element. Not only this, maybe you can also do for, yeah, then you constructed V lambda. In fact, V lambda was constructed by, you have constructed by telling that you quotient by unique maximal submodule. So did we complete the goal? That's the question. What did we get so far is we have constructed the irreducible representation. The question remain is this one finite dimensional? And what we have observed in this example is, if lambda is complex, you can't quotient even the maximal submodule here become only 0 submodule. So nothing else will be a submodule. So as it is maybe an irreducible. So V lambda, M lambda may be matching if lambda is equal. So here V lambda is, that means it's matching with V lambda. So this is infinite dimensional space, right? So very well that whatever this quotient may be infinite dimensional. The SL observation also telling you that if it is non-negative integer, then that M lambda by the maximal submodule, so this is the maximal submodule, because it has a unique submodule, this will be the maximal submodule. And you quotient it, you got V lambda. And V lambda is finite dimensional. So the goal to prove now is, if lambda is a dominant integral weight, whatever irreducible you have constructed by quotient by Verma by a unique maximal submodule, that will be a finite dimension. And to do that, I have started with an SL3C. I have a lambda which is dominant integral weight. And I have a spanning set like this. I want to do the analogy of the earlier one. Once we have a spanning set, let's understand, let's make use of this lambda is in this dominant weight. So I can go, if you want F1, I can go still F1 of lambda of H1. Okay, so that's where I went it till in this example. I went till if K is E power fkv is 0. So yeah, lambda plus 1 tak I can go, that is 0. So e power, so what I want to do here is same thing I want to do. So even we did it. So same thing. What we did is e dot, even e1. I restricting now the SL2 theory to this string. So I'm doing this, whatever this you are saying. This is again like a one more Varma module for SL2. So I apply the whatever SL2 theory I have done. So what I am getting is E1 kills F1 power lambda of H1 plus 1. So that's what I got it here. I will go back. E power, yeah, E F power lambda plus 1 V lambda is 0. That's what we proved it. So I'm using the same fact here. So the question is, so till this point, I don't have a control. They should be there. So even the next one, if I take it, this one, it is killing with E1. That's very good. So the question now is, what maximal submodule I can construct for M lambdas? Right? So I'm doing the same thing. I want to quotient by maximal submodules. I want to analyze what are all the maximal submodules. The first maximal submodule I can get it by this one. What I can get it. So you take that one. Ask the question. This is a weight vector. Submodule should have a weight vector. You have taken that weight vector. Ask the question. Will it generate? So will it generate the maximal submodule? So you have to eat with H. You have to eat with F's, you have to eat with E's. Here, not only one F, there are many alphas, many F's, many alphas. So you started eating with all the H alphas. This element will fix. F alphas, what they will do, they will generate the back ones, whatever you may get many back ones. So F alphas, this entire thing, whatever here, it is there anyway. It is because you're taking what you're looking now is UG times cyclic module generated by F1 power lambda of H1 plus 1 V lambda. You are going to say that, tell that this is a maximal submodule. Not a maximal submodule, this is a submodule. This is a. So is it a submodule? That's a question. No, it is a submodule because you are taking cyclic. And because you are, the only thing is it should be proper. So the only thing you can check that it should be proper submodule. F alphas is okay. You go back left only. You can't go back right. So you should not reach till V lambda. That's the only thing. You should not reach till this. What happens to E's actually will push this side, right? So that you may get V lambda. But good thing is if lambda is non-negative integer, E is killing it. So it can't push forward. So you got this submodule generated by this, which is a proper submodule. Okay, but one second. But other E's, there are other E's are there. The question now is, what about E2? What about E theta? They may push forward and get back to V lambda, right? So you have to question. So you have to answer that. So whatever E2, if you act on F1s, what happens E2 and F1, you want to commute it because this weight is alpha 2, this weight is minus 1. So this product is actually weight of alpha 2 minus alpha 1. So this is not a weight. So what that tells you is that E2 F1 is commuting. So if commute and push forward to V lambda and it kills it. It's very good that E2 also can't move forward. So this will be killed by E1, this will be killed by, so this vector is killed by E1 by SL2 theory. Because E2 commutes with F1 and go and act with V lambda directly and it kills. And similarly E theta. Similarly, if you do E theta, no, but good enough. I think E theta is not needed. So it's enough to check for E1 and E2. E theta it will not commute actually. It will generate another E2, but no need to check because maybe I should tell highest weight vector. You no need to check for all the E alphas. Only simples are good enough because the other ones will means in other words, see, here if you try to ink with E theta, you make use of the property that E1 is killing and E2 is killing. So E theta is exactly equals to, it's the Lie bracket of E1, E2. Right? If you, so that is same thing as E1, E2 minus E2, E1. So because E1 and E2 are hitting this vector and killing 0, so E theta will also kill the vector. So that's why these positive roots properties, all roots are not needed, only simples are good enough. But great thing is nothing will give it. So this is a highest weight vector. In fact, what you got here is this vector, whatever you are seeing there, what is that vector? F1 over lambda of h1 plus 1 dot v lambda is an highest weight vector. Highest weight vector. So because it's an highest weight vector, you take this. This is a Verma module now. This is sitting inside. This all will sit in m lambda because inside m lambda no other relations are existing. So here also there will not be any relations. So any submodule, any cyclic submodule, and anyway this is an highest weight vector. So the E is already killing. So this is only un minus will be there. And there will be no other relations anyway involving this un minus because the entire thing is sitting in m lambda. So the thing is, this is again a Verma module. So this is equals to another Verma module of weight. What is the weight of this? So the generator has this weight now. So what is the weight of this? If you write it down, what weight it is? So yes, lambda, right? Highest weight as lambda. Then when you act with F1, you have to minus alpha 1. This many times you have to minus alpha 1. So the weight of F1 power lambda of H1 plus 1 dot V lambda is equals to lambda minus lambda of H1 plus 1 times alpha 1. This is same thing as lambda minus lambda of H1 alpha 1 minus alpha 1. But do you know this S1? See, this is, it looks to me like this is a while group action on lambda. Do you remember this while group definition? So if I recall this definition from Sachin's lecture, lambda minus 2 lambda alpha 1 by alpha 1 alpha 1 alpha 1. But I already told you that this is exactly lambda of alpha 1 check. Lambda of alpha 1 check, which is same thing as h1 for me. So till this point, it is exactly s1 of lambda, but there is alpha 1 is coming. So you introduce some symbol which is rho. So what is this rho? It's an element of h star, which on h1 it gives you 1. On everything it gives you 1, in fact. In other words, rho is some of the fundamental weights. So rho is, it's very useful tomorrow also for while character formula and all. So rho is some of the fundamental weights, which on every h1 it is it's equals to 1. So the conclusion here is, when I substitute s1 lambda plus rho, what I am getting? So what is s1 lambda plus rho? S1 of lambda plus rho, by definition, it's a lambda plus rho minus lambda plus rho of alpha 1 check, that is h1 alpha 1. So which is same thing as lambda plus rho minus lambda of h1 times alpha 1. This rho of h1 is 1. So you are getting one more alpha 1, which I wanted. Because there is a one more alpha 1 is there, I introduce this rho symbol. And so far is everything. This will be, so this and this I want to match. Right? So this here I want to match. So they're almost same, but there's a row extra is there. So if you subtract that row, so whatever that you are getting is here itself. So this is the weight of this module, and this has a nice notation. It's very useful in tomorrow's class also. This is dot action. So S1 dot lambda. What is S1 dot lambda? This is a notation. It's S1 of lambda plus rho minus rho. This dot action is useful tomorrow also. Even in the Harishchandra theorem, this is useful. So what you proved just now is M S1 dot lambda is contained in M lambda if lambda of H1 is non-negative integer. Similarly, if lambda of H2 is non-negative integer, M S2 lambda is contained in M lambda. So this is for every I, even I to L. So whatever Si lambda, maybe I'll erase everything. So you try to get some maximal submodules here, not maximal submodules, many submodules you are trying to sit. So the beautiful here is one Varma is sitting inside another Varma. Right? So Varmas can sit inside another Varma. There are many Varmas are sitting in fact. And what you do, you sum them. So this sum and this is a submodule again, and sum of all the proper submodules is again a proper submodule which is sitting inside M lambda. And the fact is, why you need a fact? It's even we can prove now. This is a maximal submodule. Maximal proper submodule. So you quotient by that. Why maximal? So it's still a question mark. Let's try if we can manage it to prove. So this maximal submodule, if you quotient it, you get a V lambda, right? And to show this is maximal, it's enough to show that this entire thing you look at. Suppose I know this is a finite dimensional. So the question is in fact nothing. So I till now I have not even proved that V lambda is finite dimensional. Maybe showing this whatever this circle module, if I show it is finite dimensional, it's an easy observation. Finite dimensional highest weight module is always irreducible. So because it's finite dimensional and you're quotienting by a highest weight module, so this will be again highest weight module. Finite dimensional highest weight module is always irreducible. I know that, so there is a unique irreducible corresponding to lambda. So this must be isomorphic. That forces that this is the maximal proper submodule. So this you are answering by showing this is finite dimensional, and this is an easy observation which we will do in the assignment exercise tutorial. Okay. So to show that is fine. So suppose if you show this, that finite dimensional and these are isomorphic, what you are exactly proving here is V lambda has a defining relations. The M lambda has a defining relations, namely E alpha kills H as an eigenvector. And whatever this quotienting by these relations is exactly, if you see that modules, the modules are generated by these vectors. So these vectors you are quotienting. So the another extra relations you are getting is these relations. So they should be zero. So you are in fact proving that V lambda is a cyclic module generated by small v lambda with kills E alphas, eigenvectors for H alphas, and F alphas. You have to put some relations to get finite dimensionality. Lambda of H alpha, even I only. So it's enough to show only at I. So for every I. So this isomorphism is also gives a defining relations for V lambda. So only these, so apart these two are Varma relations, and you divide by few more relations, L, that's it. You get a defining relations for it. So the everything is now boiled down to prove why this is finite dimension. Okay. So how the proof goes in this? So the idea of the proof to show this is finite dimensional. Enough to show its weights are finite. You remember this highest weight modules will break down into direct sum of some weight spaces. Weight spaces will be less than or equal to lambda, and each weight space is finite dimensional. So if you know that the it weights are finite, so only it has only finitely many weights. You are concluding that each weight space is finite dimensional and there are only finitely many weights. So you get this is a finite dimension. So how do you show that its weights are only finitely many? So the weights of V lambda, weights of this are actually contained in fact equal. This is a while group orbit, while group on mu. So you know already lambda is a weight. See what you are going to show now is uh, mu is in fact a dominant weight. So what is your claim now? Your claim is weights will be contained in this set. The observation is this set is a finite set. What is this set? This set is telling you take a dominant weight. Under dominant weight, they are all less than or equals to, right? So you have seen this picture, which is it is in a cone, right? It is in a fundamental chamber somewhere. The lambda is somewhere, and then the mu will be below it. So there are only finitely many dominant weights are there below it. Integral because it's integral and under the so there are finitely many, and this is a finite group. So the orbit will be finite set. So this entire set is finite. So the weights will be finite. Now to show the entire set is finite, how do you show? So the enough to show that dimension of this weight space, muth weight space, is same thing as dimension of W mu space for all while group elements. This is a very good statement. What if mu is a weight? What you are proving is if mu is a weight, W mu is also a weight you are proving for any while groups. Okay? The statement, if you understand, if something is a weight, its while group orbit is also entire orbit is a weight of this with the same dimension, in fact. Okay, and if you show this, so what are all the weights now? They are all mu in H star actually at present, and it's all while group orbits. But you know, while group orbit will take any element in H star, it pushed to fundamental chamber. So while group orbit any always have a dominant weight. That's why it's enough to consider only orbits for the dominant weights, and weights must be less than or equal to lambda. So this proves that. So this is what you have to show. Because while group orbit, every while group orbit contains a dominant weight, all the weights will be exactly equals to all the mu's in H star and its while group orbits. But mu's in H star will give you a one dominant weight, so enough to consider dominant weight. Okay. Maybe this proof to this proof is so there is an automorphism actually which tells to which maps to this and that automorphism makes sense. Maybe I'll write down that automorphism. It's very useful. So this is you have seen already this automorphism exponential of if rho is a representation rho of xi exponential of rho of minus yi exponential of rho of xi again. This automorphism actually takes this is Ri. Ri takes, it's an automorphism. Actually, this is an automorphism from entire between these two modules. So you can assume. But only thing is why this is nilpotent. See this. What is the meaning of this exponential? If these are nilpotents, you can make as exponential. We have already used the preservation of Durand decomposition. This is a nilpotent, but I know that this is nilpotent if I have a finite dimensional thing. So I don't know about the finite dimensionality still. So what is the meaning of acting on a vector? So the thing is, what is that you have to show? You have to show it's locally nilpotent. Means how do you show something is locally nilpotent? Mm. So what is that you have to show? You have to what? Yeah. So this action makes sense on this. So that's what you have to show. This Ra makes sense and which converts from here to here. But this is not a finite dimensional. You don't know still. No, weight spaces are finite dimensional, right? That's correct. But that's why these weight spaces are finite dimensional. You take a vector. This lie in only some finitely many. I think here itself you can consider this picture. I think. Okay. Anyway, I'll stop. So there is a way to act on a V because they act in a locally nilpotently. Because if you see this picture, I think I have drawn this picture only for that purpose. If you on this F1, any Fi on this, it acts by Fi lambda plus 1. And on this entire string, each Fi act with lambda of hi plus 4 times it kills. On the entire this string, so if two F's are there, it acts by, if you act with lambda for 3 times you add it, so 7. If you add this to this, on the entire weight space vector, it will be 0. So it's an easy observation. So what you are checking is every vector, it will be killed by bunch of Fi's acting, and bunch of Ei's acting definitely kills because there's a weight bound. So Ei's, you can't go behind W. So Fi's and Ei's will locally nilpotently act on every weight vector. That's why this operation makes sense. This operation makes sense. That's what. So then this automorphism takes mu weight space to W mu weight space. Okay. But this is very useful fact. So the summary we are seeing is, if you have a irreducible representation and it mute weight space, dimension, and because this is my m lambda finally, right? Finally, this is my v lambda, and this is what you're proving. So this is very useful to make a character. This implies, in fact, this is same thing as character is a symmetric polynomial, or in other words, character. So we'll see tomorrow. Character is, so this information is very useful to tell that character is W invariant. In SLN case, it's a symmetric polynomial. Okay, so soon we'll continue tomorrow about this. Thank you. Any questions? Okay, thanks. See you after half an hour.